requirement as well as commercial and industrial requirement. Among all these sources, this electricity has been found one of the most reliable, affordable, efficient, and clean, just because of the reason being easy to control. And our dependence on electricity is increasing day by day, just because of this increasing urbanization, and with the achievable targets in future for the development of smart cities, this requirement of electricity is definitely going to improve. The International Energy has forecasted that a 30% increase in world energy demand is expected by 2040. So most of this demand till now was fulfilled using the fossil fuels, which are usually coal, oil, and gas. And this energy conversion process was utilizing the burning of this fossil fuel as step one, then releasing heat energy, and then converting it into electricity. But this conversion process was causing increased greenhouse gas emissions, which were a critical challenge and a point of concern for the environmentalists, just because of their increasing concern about the climate change. So this climate change is a different dimension of research, and definitely people are thinking much more about this climate change, because they feel that this climate change is associated with some other problems at the global level, like 1.5 degree increase in the temperature, and definitely that is going to melt all the ice and this increased sea level, etc. And definitely a sufficient threat for the cities who are situated near the sea shores. And definitely these greenhouse gas emissions were going to increase these global warming issues in summary. So to overcome these problems, the solution was proposed as avoiding the use of this conventional sources such as fossil fuel based burning of those fossil fuels, and shifting on this renewable energy resources, for example, solar, wind, biomass, hydro, and tidal power. So these attempts have already been started since long, and since last at least 4 or 5 decades, we are trying hard to shift on these, and presently we can say that we are very close to the given targets, as some countries have already declared by this particular year, like 2030 or 2035, they will have the complete generation of electricity from the non-conventional energy sources or renewable energy based resources. So that is a good sign. The goals given to us under this United Nations Sustainable Development, that is Goal 7, also work towards this, and this promotes the installation of renewable energy resources across the globe. So if we wish to define these renewable energy resources, so this renewable energy is defined as energy produced from natural processes, those resources which are inexhaustible. So these renewable resources offer solutions due to challenges of rising electricity demand. I have already discussed the reasons for them, without any global warming threat, with environmental sustainability. Yes, that is a key word nowadays, sustainability, and with ability to provide power to even those remotest areas which are still deprived of the conventional sources of electricity. And definitely those are underprivileged persons whom these renewable resources are providing electricity nowadays. So if we define this renewable resources, we can say that this classification gives as hydropower, solar energy, marine, bioenergy, geothermal, and wind energy, and their conversion to electricity sources for them can be given as for hydropower, this renewable hydropower, mixed hydro. Solar energy means concentrating solar power or conventional solar PV, this power, solar PV plate based, which is rooftop, available on the rooftops. Then marine, they give as waves, energy, tidal energy. Then bioenergy is municipal waste, biogas, biofuels, biomass, etc. Geothermal is a standard mode, and then wind energy. Wind energy is available presently through these wind turbines installed offshore and onshore. Offshore is also sufficiently developed in the this western part of the this Europe. They have already have access and sufficiently amount of this wind energy. Offshore wind energy has already installed. So this renewable energy resources can be classified by their characteristics, uh, which they do not have, such as dispatchability. So this, what does dispatchability mean? Dispatchability refers to the source's ability to adjust power output in response to system requirements, right? So how to make this non-dispatchable source of renewable energy resource based energy or electricity, this, because this non-dispatchability is due to this variable renewable energy, because these, all these sources, they are intermittent in nature and they are dependent, their generation is dependent upon the climatic conditions, but they are made dispatchable nowadays with the use of storage. And the storage enables the characteristic of dispatchability of these technologies. Clear? So here's some data which clearly mentions that these renewable energy resources are continuously increasing, and different papers and different websites, they are continuously highlighting this emergence of new technologies and new installations of these renewable energy resources. So there is no need to go in detail. I think we all believe that this is continuously increasing. This is also a data taken from the IEA website for in megawatt capacity, and this finally this total gigawatt capacity up to 2020 is established with this website and different resources papers of 2021 and 2022, and it clearly indicates that between this decade of 2010 to 2020, this total gigawatt hydro capacity was increased from 238 to 1590, and total including hydro, this complete energy was 1164 to 2802. So this is a huge multiple times rise in this capacity of generation through renewable energy resources. And this clearly extrapolate the projections up to the 2040 in as per the given policy scenarios which are presently implemented in India, and it indicates that from 2000 to, which is the level of almost 100 gigawatt, this is going to up to the range of more than 1800 gigawatt in up to 2040. So these are the projections which are made and which are temporarily modified, also given in the due to just because of some restrictions or some favorable conditions of policy and the installation. Here I wish to inform that in some conditions, some literature on related material, it does not include large hydropowers as RER, because it claims that these large hydropowers, they have extensive environmental impacts and they have some associated emissions which are almost equal to of greenhouse gas emissions to the conventional water resources, conventional power sources like coal, etc. And in support of this, it gives a reference of this 2004, in which a study was conducted in Brazil, and they say that experimental measurements were made to determine that the gas emissions through bubbles formed on the lake bottom by decomposing organic matter and rising up the lake gradient by molecular diffusion. And they clearly measured those emissions and they concluded that they are almost equal to the greenhouse gas emissions of the equivalent coal power plant generation. So that is the reason in literature these large hydropower plants are not considered as renewable energy resources. The integration of renewable resources directly into the grid is a challenge due to their intermittence, randomness, and the uncertainty just because of the climatic conditions. We all know that due to just different environmental conditions, different geographical conditions, these are giving different generation. Same technology is giving different generations at different locations and in different seasons. Now, second term is what is DER? How this RER and DER, they are related or they are not related? This is the question. So I will just try to explain you that what is DER, distributed energy resources, right? Basically, if by the definition we go, we can clearly understand that these distributed energy resources, they are the on-site generation sources in distribution system, which are connected to the distribution system through some uh, point of common coupling, or they are available commercially also, they are available in residential, with residential customers also. So what are these DERs? This may be an RER, right? So this renewable energy resource is a subset of the term DER. Clear? But it is not limited only to the renewable energy sources. It clearly indicates that DER can be a conventional power source also, like micro conventional generators consuming gas or fuel, and then energy storage systems. They also come in this distributed energy resources. And the uncertainties related with the renewable resources, they are overcome uh, through the use of energy storage systems and micro conventional generators, which make these renewable DERs a dispatchable source. So these DERs cover a wide range of technologies and services both. If we go in detail, we can find that renewable, among other than this renewable resources, energy storage also comes into this. Electric vehicles, which are treated as the battery on wheels, they also come under this. Then different technologies, they also come within this, and different instruments such as air conditioners, hot water systems, pool pumps, and other smart appliances, they also come. These technologies or services also come under the category of DER. And as I told you earlier, that this DERs can be located within a customer's premises as a behind the meter facility, or they can directly connect it to the distribution network through a point of common coupling. And if we deal with these DERs, what are the advantages of DERs? They are almost similar to as per the characteristics, like they are having high efficiency and energy production savings, because they do not have to bear these losses in the transmission and distribution. They have this environmental protection, because this damage because of that is not realized by the long transmission lines. Number two, the intermittency is covered by the use of this energy storage systems and other means. Then this reduction of transmission and distribution losses are also there. They support the local power grid for improving the power quality also, enhance system stability and reliability, because they are locally available in abundance. Deferral of generation, transmission, and distribution capacity investment, because by development of a local resource in some local area of higher power consumption, that defers the large investment of new transmission line, new substation, and new generation station at some remote point. They also provide this VAR supply or voltage control, other ancillary services that we are not covering today, but they also support the ancillary services which are providing financial support to the customers through some regulatory modifications which have been announced recently. Then, as I told you, this is giving you a PQ environment improvement such as voltage improvement, power quality improvement, phase lag lead compensation, etc., etc. Then combined heat and power generation is also provided through these DERs, because in some cold countries they need this heating arrangements also along with the electricity. And definitely these DERs give the advantages of demand reduction. They also bring down the maximum demand from some higher point to lower point when these are used in conjunction with the main grid. And they also provide standby generation in case of grid failure. So the integration of DERs into distribution network requires three major steps. Number one, the optimal sizing. Number two, their control and scheduling of participating energy resources, which are the main themes of research in the area of DERs and their integration. And definitely, here comes the term microgrid. That is the term which integrates distributed energy resources in them. And definitely, microgrid is a system which you can say which has the capability to operate in islanded mode and as well as grid connected mode, in both the modes, when and where, as and when required. So definitely now we will try to understand something about the microgrid, because this microgrid has a controlled combination of renewable resources, definitely in terms of DERs as well as storage, which are the main focus areas for today's lecture. So these microgrids are referred as next generation power systems. They are considered as subset of the smart grids also, and they have integrated themselves as DERs, energy storage systems, and a variety of loads, right? So this they are having this communication links also in between all these things, so that a proper control can be implemented between them. And this application of MGs can also be found in Internet of Things, Industry 4.0, smart cities. And if you have a recent literature review, you will find some papers in the area of ship microgrids. You will find some papers in the area of satellite microgrids, and uh, and other very small areas of application where these microgrids are used for providing reliable electricity, which is capable of giving electricity in case of main supply failure, and properly manage the given resources for fulfillment of load requirements. So what is the definition of microgrid? I will definitely try to limit my discussion to the basic two definitions of the microgrid. Given by the one is given by the US Department of Energy, and second is given by the SIGRE. I hope you are aware with the term SIGRE. We will explain it later. So US Department of Energy, the basic definition was given in 2012. This is treated as the one of the basic definitions. It defines microgrid as a group of interconnected loads and resources. Which resources? Distributed energy resources. So it clearly says microgrid has sources as well as loads. Then with clearly defined electrical boundaries. Means geographical location is defined. It is not going beyond that given electrical boundary in that geographical location. And it has a capability to act as a single controllable entity connected to the main grid at some point of common coupling. Means at a single point, it is connected with the distribution system, right? So as and when required, it is connected to the grid in the grid connected mode, or if the grid is not capable in a position to supply electricity to this system, then this microgrid is not without power. It can manage its load requirements through its controllers uh, and work sufficiently or efficiently, rather we shall say, in islanded mode. So this definition given by the US Department of Energy describes three requirements. One is identify the part of distribution system. Means it is not a separate entity, it is a part of distribution system, which is MG and a microgrid, and it is not distinct from the rest of the system. Resources connected to a microgrid are controlled with each other. Number two. Number three, it may work as in a sufficient manner, either it is connected or not connected with the grid. So these three requirements, it clearly mentions along with that geographical boundary condition, because that is similar for all the microgrids, right? But this definition is not saying a single word or any requirement about the size of the DER. Means microgrid can be right from the kilowatt size to megawatt size. Okay. Number two, which type of technologies? Means only RERs or only non-conventional resources or a combination of conventional and non-conventional. Any set of combination may form this microgrid, right? So this is the very broad definition covering defining the different requirements without limiting the size is given by this US Department of Energy. But this SIGRE definition was given by this SIGRE working group. It clearly says that they are electricity distribution systems, right? Similar to the previous one. Second, they contain load and DERs, similar to the previous one, which can be operated in a controlled and coordinated way, similar to the previous one. They are also talking about the controlled way without either in grid connected mode or in islanded mode. So if we talk about if we consider the basic requirements or the basic salient points of the definitions, they are almost same in both the definitions. Clear? But where they are different in terms of requirements of this renewable resources. Focus of the SIGRE definition is more on the renewable energy resources, and the focus of the US government definition is more on the fulfillment of requirement or more about the reliability of the power system. So this is the basic difference between the microgrid definitions or targets about this European concept and the American concept. So if we talk about the basic microgrid components, as we have already discussed in last two definitions, we can summarize them as they have 5 key components: energy sources, energy sinks like loads, means for connecting or disconnecting for larger power system, definitely a control switch, which control switch at the point of common coupling. Then comes a control activity for this control of microgrid, and then protection of microgrid. So definitely you will find that right now, if you are working in that area of renewable resources or their control, you will find that there are different types of paper nowadays appearing for the protection of microgrid, AC microgrid, DC microgrid, and controlled and islanding detection, etc., etc. These are few areas which are continuously researchers found them of their interest to explore every day, and they are keep on exploring, and literature is coming, and new researches and new technologies are appearing on daily basis. What are those 5 critical functions of the microgrid? Number 1, nature of connection. Number 2, precise energy balance. as it indicates that it can work efficiently in an grid connected as well as islanded mode. Third is energy storage, so that the intermittency of the RERs can be compensated. Then comes the demand management, means balance of power. And then seasonal match between generation and load, because we all know that the load requirements as well as generation of human resources, that all varies with the seasonal change of seasons. In winter, the load requirements are different. In summer, load requirements are different. Similarly, the with the change of season, the climatic conditions are different, environmental conditions are different, and so the generation through this RERs, that also changes, right? And the same five critical functions, they have been denoted here or shown here pictorially, so we will not go in detail with this. Next, different types of microgrids. What are the different types of microgrids? Different types of microgrids are, this clearly indicates you that this diagram, if we will try to describe this types of microgrid, which are classified in the four categories here. So one very basic fundamental unit is given as separate island grid. This is an example of city, village, or island outside utility grid, and its capacity may be up to from minimum to 10 kilowatt. Then comes a low voltage customer microgrid, means this requirement is limited to a single customer, but the size, handling of the power capacity requirement, they may be a bit larger and they may go up to 10 to 100 kilowatt. Then comes a cluster of this type 2 microgrids, and that becomes a low voltage grid where multiple customers, they are connected in a subset. And this LV network includes many DER units and many customers, and that may go up to the range of megawatt. And definitely this several low voltage microgrids, their cluster makes a medium voltage feeder microgrid, which is connected to a MV or HV substation, and through transformer that is connected to the main grid. So if we try to define them one by one, so this number one, separate island grid, this is a combination of DG units and energy storage units, as you can see in the diagram. They provide enough electricity for one customer or a small community, you can also say, that separates from the utility grid, because its remoteness often makes it difficult to make their connection from the grid. And this is number two. This particular number two is a subset of such grids where is a low voltage customer microgrid that serves the power demands of one customer, like a farm or a detached house, by the connecting and operating parallel to the grid. Then when there is a fault in the utility grid, the customer power needs are met by one or two of their own DG units of energy storage in islanding mode. So this is also connected to the grid, but it has the capacity, self-sustaining capability of being dependent on the energy storage, which is a part of it. Because you can see it here that this transformer is also here of being a low voltage capacity, and this micro turbines are there which are connected to different gas. They are also having this biogas or some storage capacity, etc., etc. Then this becomes the third case, right? And this brown dotted line indicates the third case, right? And this third case indicates that this is a LV microgrid, right? So this is one LV microgrid, this is another LV microgrid, and these type 3 microgrids, they are characterized by a group of LV customers of type 2, where power production is based on many small scale generations like this wind power or other sources. There may be some solar powers also, like solar panels on the roof of houses, and some micro turbines also, as shown here. So they may be of the range of bigger cities or they may be of the bigger communities, this LV microgrid can range from just a few consumption points to an entire LV network fed by this MV or LV transformer, which is placed here. Then finally comes as this HV or MV network, which is connected to this MV feeder microgrid. This connected through substation through this microgrid, and this is the highest capacity case of microgrid. So there are centrally connected at one HV or MV substation, and they can consist of partial or the entire output of the HV or MV substation through microgrids, right? So these four cases represent the four types of microgrid as shown here in the diagram, and imply that microgrid uh, microgrids can appear in a variety of scales, right from some say very small capacity of kilowatts up to the tune of megawatts, right? So this microgrid grows in scale also. They can multiply also, implying a greater number of this implemented distributed generation and energy storage units. Their balancing capacities and controllability also improve with it, since it will be less sensitive to the this intermittency of the renewable resources on the load demand and supply of electricity from these DGs. Also, this size of the microgrid, as I told you about these four cases, that is also related to its connection voltage level. And LV customer grid will typically be connected to the low voltage main grid, while this LV microgrids that include many DERs and several customers that may be connected to the MV voltage level. And finally, this MV feeder microgrid may be connected to this high voltage substation also. And if we talk about as the scope of the lecture also includes this grid energy storage technologies. So different energy storage technologies include this electrical, electromagnetic, mechanical, thermal, hybrid energy storage, and electrochemical also, right? So this electrochemical that consists of these batteries, right? And there are different types of batteries up to the very newest technologies such as lithium ion, lead acid, nickel cadmium, etc. And lithium ion is recently it is getting a lot of hype just because of this advanced characteristics and heavy capacities, large capacities in a smaller size. That's why they are getting preference nowadays in their application in right from the mobile, laptop, or up to the level of this R storage, electric vehicle storage, right? So we all are aware with these different types. We have read them several times that electrical energy storage is an electrochemical capacitor, electromagnetic is SME storage, and this mechanicals may be this hydroelectric storage, pumped hydro storage, compressed air, flywheel. They have their own different characteristics. Then thermal may be of high temperature. They might be classified as high temperature or low temperature energy storage. For high temperature, the storage capacity or the example is molten salt. And for low temperature, this ice storage, etc. They are the examples of the storage of energy. And the latest trend is the hybrid energy storage, where we couple two or more energy storage technologies for improved efficiency or improved results where the energy storage is required. And several new papers are coming nowadays with the title of this hybrid energy storage. Rajiv ji, am I audible to all?
Sir.
Okay. So this particular generation and storage options may be summarized in an overview form. This generation, like conventional and non-conventional, if you see, we are talking about this DG sets. So DG sets are the oldest resource, most reliable in last decades. We have found that they are always ready to serve. Just by a click or rotating their starter, you can start them, right? So they are the most reliable, dispatchable, load following, whenever your load is increasing, you can start the second one or third one. And the startup is also quick, right? And they are also capable of giving this combined heat and power requirement fulfillment. So these are the advantages. In terms of reliability, they are the most trusted one. But disadvantages are they are producing noise. Nowadays, they are using this canopy for this noise reduction also. But they are the largest source of this greenhouse gas emissions, and specifically this particulate emissions such as nitrogen oxide, etc. So nowadays, technology-wise, they are not preferred, at least when this uh, uh, we talk about this climate change, or we talk about this air quality index. So we have to criticize them just because of their disadvantages. Then comes this micro turbines. They are also a constant source of power, which has dispatchable power. Definitely, they are having lesser emissions in comparison of DG sources, and mechanically they have a simple construction, and they have the multiple fuel options depending upon the local requirement of local generation. They can be fueled, and they are also combined heat and power capable. So these are the advantages. But again, the disadvantages of that greenhouse gas emissions is their disadvantages. Fuel cells, they are the relatively newer technology. They are providing a constant source, so they are dispatchable, CHP capable also, combined heat and power. And the best advantage which they have, that is zero on-site pollution, right? Because we all know that they use hydrogen or water resource as a fuel for generation. Their initial cost is high, but once it is there, proper maintenance is there, they can run without any consumption cost, or their or any recurring cost they can run. But initially, they are relatively expensive, and their lifetime is also limited because of all these chemical reactions taking place inside. So different technologies which are fuel cells, you can find them here as solid oxide, molten carbonate. This is phosphoric acid, alkaline, and low temperature PEM technologies. They are the most common technologies of the fuel cell nowadays. Then finally, this comes as RES generation, which is the scope of this lecture today. That is solar PV, small wind turbine, and mini hydro. They are also the source of generation, right? And definitely they are having better efficiency than this micro turbine. Uh, of course, these renewable energy sources based generation that has zero fuel cost. Once it is installed, it can simply start producing electricity on the basis of on consuming only the nominal maintenance and operation cost, and they have a advantage of zero emission also, right? But again, the limitations or disadvantages can be given as they are not dispatchable without the storage, which is also having some cost, initial cost also, and maintenance cost also. And definitely, if you are not using them if you are not using them with the storage, they are variable and not controllable, right? So these are the few resources, few technologies available with this thing, with microgrid. Second comes the storage capacity. This storage things are there. They are the batteries, flow batteries, hydrogen from hydrolysis, and kinetic energy storage, flywheels, etc. I have already given you a better classification than this. But if we talk about the advantages and disadvantages, we can say that batteries, they are have a long history of research and development, and but these batteries have limited number of charge discharge cycles, and their waste disposal is not problematic for older technologies such as this lead acid batteries. They are almost fully recyclable, but this problem is there with this lithium ion and nickel cadmium. Their recycling is still an issue, and there are several concerns about their recycling until unless a proper recycling pattern or process is developed for them, it is a challenge. Then comes the flow batteries, which are also known as regenerative fuel cells, right? And they are having the advantage of decoupled power and energy storage, and that is able to support continuous operation at maximum load. That is an additional advantage of these flow batteries, but they are still at an early stage of deployment. Being a newer technology, they are costlier also, and these are some basic limitations. Then comes this hydrogen from hydrolysis. This hydrogen is a very common and most talked technology nowadays after this electric vehicle technology. So nowadays there are several papers available, several prototypes, researches are available for the hydrogen storage and their usability for different energy requirements, right? So this is having an advantage of being clean and quite efficient, but still there are certain limitations just because of the lack of infrastructure developed. They are still showing low end-to-end efficiency, right? And this storage of hydrogen is still a challenge, right? And I was reading somewhere that this like what is the difference between this vehicles which we are using as a CNG based common vehicles, IC engine based vehicles, and what is the difference between this hydrogen fueled electric or hydrogen fueled vehicles, right? So this refueling and this storage of hydrogen, that is a basic challenge, basic deterrent for developing this hydrogen as a fuel for vehicles, right? So if once these limitations are being addressed properly and they are commercially developed up to a level of a cost efficient level, then you will see that this market will be full with these hydrogen vehicles and use of hydrogen as an effective alternate for the fulfillment of our energy requirements. Then finally comes this flywheels. Yes, they are showing fast response. We are aware with this flywheels right from the early days. These are the mechanical devices which are having this high discharge, charge discharge cycles and high efficiency, but they cannot be stored for a longer period just because of their high standing losses, and their discharge time is also limited. So even being so much having so much advantages, they cannot be a reliable resource if they are to be used after a longer gap, after a sufficient gap between this charge and discharge. They are not that reliable. Then we are more focused about this battery energy storage system for this our dependence on this for making our renewable resources dispatchable. So definitely we must be aware with their elements. So if we talk about the battery storage, the elements are their modules, their racks, and the cost per kWh. Then another aspect is battery management system, where this battery management and BESS protection, that is also a very challenging task, because nowadays we are hearing a lot in the newspapers and reading a lot in newspapers or in the news about this fire, right? These electric vehicles nowadays, either two-wheelers or four-wheelers, if they are not properly maintained or not properly taken care about discharging, they may catch fire. And such events are happening on, and we are reading them on the daily basis in the news. So this is an area which has still a scope, sufficient scope for improvement. So this element is an important element to address. Then comes this power control system, where this bidirectional converters, inverter control, interconnection, and this switch gear for the protection, and definitely cost per kilowatt for this assistive infrastructure. That is, they are the concern. They are point to be addressed in this particular element of battery energy storage systems. Energy management system, we all aware with this. Keep energy management system is a very lucrative area of research among the researchers, and they try to find out the different constraints, and by deciding their objective functions, they try to minimize different costs, different losses, and try to maximize the advantages obtained from this microgrid system, etc., etc. So discharge, load management, ramp rate control, grid stability, monitoring, and the cost of energy storage system. They are the main considerations for this specific element regarding BESS. Then comes site management systems and balance of plant, etc. They provide you sufficient supportive infrastructure for implementation of these technologies, or their implementation for very large scale, so that they may be sufficient, they may give sufficient support for larger support of the grid side storage, etc., etc. So those things, at the level of microgrid or at a level of a multi-microgrid project, they may be of point of concern, and they shall be addressed. So a microgrid helps in achieving objectives of efficient transformation of passive networks by participation of the consumers. Some of them become prosumer, so this passive network becomes an active network. And there is a continuous requirement of bidirectional power flow and its control. And this storage acts as a supported source for reliable and continuous supply, then power quality enhancement and clean environment, right? But the requirement for this flexible operation of microgrid, we cannot do it if we are not taking the support from this power electronic interfaces and different control technologies of microgrids, or inverter control technology, or energy source control technology. So there are different type of control technologies are involved for this flexible operation of microgrid. So MG offers several advantages such as environmental advantages, operation and environment, power quality, market, etc. We will not go in detail because we have already discussed the advantages of distributed energy sources, and they are almost similar to these advantages. But MGs have some limitations, and they are the point of concern because our future research or future solution providing capabilities require to address these limitations, right? So few of them are optimal use of energy sources, control issues, lack of system protection and regulatory standards. They are still not available in few countries, and customers' privacy, right? Some customers are not ready to be the part of this microgrid and network infrastructure because they are more concerned about their privacy, so that if they will have to disclose the amount of their generation and consumption both, then only this like energy management is possible, and they are not, and they take as a breach of their privacy, and they are not ready to be a part to participate in it. Efficiently using the research, but few of them cannot be because basically they are the mindset problems and they cannot be addressed. So we will leave this. Basically, this deals with the microgrids basic. When these microgrids were started, we will just jump from here, right? And but we can tell you that even basically one thing I would like to address, that the basic father of this microgrid term, he is the Robert Lassater. Robert Lassater was a researcher from University of Wisconsin-Madison, and he basically termed this network of renewable resources with some effective control and with some patronic interface. And when he developed this network of all these things, and he gave them the name of microgrid, right? And his basic research was available in this paper named as where is the basic paper? Yeah, this is the basic paper of Sutter, which was published in the IEEE PES winter meeting, right? And this was the year 2002, right? And you can find these two articles in IEEE Explore, where you can find out that these are the two basic documents which were the presentations made by Lassater, in one in the IEEE PES winter meeting in 2002 in United States of America, and second he made the presentation in Germany in 2004 with the title Microgrid, a Conceptual Solution. So these are the two initial literatures where the term microgrid is available, and that was used by this particular person who was the inventor of, you can claim, you can say that he was the first person who developed a microgrid and described this as a controlled entity of a single unit. Now, different foundational researches which were developed or started in United States of America as well as in Europe, the basic projects were named as CERTs. Number one is Consortium for Electrical Reliability Technology Solutions. This was the name of the project of United States of American project. And second project was started in Europe. That was the name microgrids, right? And the second phase of microgrids was followed after this first project was completed. That was the name more microgrids, right? The phase one was microgrids and second phase was more microgrids, right? Very interesting thing. So if you want to know about this third project, this is having its own website, and this is certs.lbl.gov. This is an American project. This is having the members: Lawrence Berkeley National Laboratory, Oak Ridge National Laboratory, Pacific Northwest National Laboratory, Sandia National Laboratories, then PSERC and EPG, right? So if you want to go in detail, you can visit this website, but I can summarize you that this was formed in 1999 to research, develop, and disseminate new methods, tools, and technologies to protect and enhance the reliability of electric power system of the United States of America. And the efficiency of competitive electricity market was another target which was to be developed with the help of these microgrids, right? So this CERT project is recognized as the origin of the modern grid connected microgrid concept, right? And this CERT paper was published also in 2002 in IEEE summer meeting, right? So this was also published in the same year when the first paper was presented by Lasseter. And this CERT project envisions MG that could incorporate multiple distributed energy resources, yet present itself to existing grid as a typical customer. As I earlier told you, that microgrid are defined as a typical load or entity which are connected to the distribution system through a point of common coupling, and there it fulfills that requirement. But in case of CERT project, this emphasis was placed on seamless and automatic islanding and reconnection to the grid. Means whenever it is shifting from grid connected to islanded or islanded to grid connected, there shall be no power outage. Means a reliable operation of the system was the priority, just to avoid those power outage conditions, right? And for this, more emphasis was placed just to handle these issues, just to address these issues. The emphasis was placed on reactive power versus voltage strategy, active power versus frequency control, and power flow versus frequency. So these were the primary control strategies which were focused in this CERT project. As I told you earlier, that emphasis of the American projects was nowhere related with the environmental concerns, right? This particular objective, basic objective was to improve reliability rather than reduce greenhouse gas emissions. No, it was not, right? And option was there to include RERs, right? But not a compulsion. This point is a basic difference between the CERT of American project and microgrid as a European project. This second, now I'm going to discuss about this microgrid project. This is name is microgrids, right? And the website is www.microgrids.eu, right? And this was a project which you can see here that it was having different partners of total 22 partners from 11 EU countries, right? And here is a list of countries with different organizations in which you can find that there are several universities as well as industrial partners also. So it was a joint venture of different natured stakeholders who were interested in developing the microgrid to handle the technical challenges such as safe islanding and reconnection practices, means better control, energy management, control strategies for a smooth transition between different scenarios of islanded and grid connected, then protection and communication so that control can be implemented easily and operation can be made smooth. So if we compare this, there was a paper in 2010 which gives an overview of these two motives of these two projects, which is this microgrids and CERTs. It compares that the objective of European and US projects, reliability of power supply was the motive of US, not European project. Reduction of environmental impact electricity supply means lesser CO2, lesser greenhouse gas emission. That was the motive of objective of this European project. Reduction of investment in plant equipment and cost was motive with USA, not with the European. Increase of energy efficiency was a concern for both the projects. Ensure diversity of energy supply. Yes, both of them were concerned, but not sufficient literature is available about that. Diversity was, you can say, the different types of RERs or DERs, right? Then power supply to island and or remote site was a scope in Europe, and right through capability provided by energy storage just to ensure more reliability. That was the concern for both the projects. So this is a summary presented by this particular author by analyzing some different papers or different projects. That maybe you may take it as a vision or the summary or the outcome of the study made by this researcher, and you have every right to differ from this comparison. So I will be more happy if you can read more about these things and come with some different conclusion. Then the microgrid classification is power type. This is AC and DC. Then supervisory control type, centralized, decentralized. We are going to study more types of detail controls in the later slides. Then comes operation mode, islanded and grid connected. Then single phase or three phase or application wise, we can find them. I will show you a list of different installations where you can find them at residential, commercial, industrial, military, municipal, or utility level. So that can also be a basis of classification for MG deployment. Architecture is different. If we talk about the microgrid architecture, clearly indicates this. It is having different DERs, responsive loads along with some critical loads, right? So this is connected through main grid through a point of common coupling and grid connected as well as islanded mode, right? So here you can find out this microgrid control. That is, you can see that with this diagram. I have taken this diagram from this particular paper of 2021. It clearly indicates that microcontrol system can be classified into four different types of controls. One is control architecture, which is classified as centralized, decentralized, and distributed. Then we can talk about control methods, which say that with communication, without communication. Then control mode. They can also be classified as master slave, peer to peer, combined mode, etc. etc. And then different control levels. And those control levels are primary, secondary, and tertiary. They depend on the time implementation requirements of control, right from the seconds to minutes, or in the level of bandwidth also. So MG's control objectives consist of independent active and reactive power control, correction of voltage profile, fulfillment of MG's load dynamic requirement. MGs require proper control strategies for macro source and load controller, microgrid system central controller. We will definitely use it. We will compare it with other formats also in a comparative table with the help of a diagram. Then comes distribution management system. And the core functions of MG control are of three sections: the upstream network interface, MG control, and protection and local control. So if these all three are not synchronized, then definitely the microgrid is not going to be successful in their operation in grid connected and islanded mode one by one. Yeah, yes, this is a diagram which shows you a microgrid architecture. Any microgrid is composed of different DERs, responsive loads, and critical loads, as shown in this figure. Here you can find that this microgrid is connected to this main grid through this point of common coupling, and this is a switch, right? And this switch is a point of connection, or you can say the control of connection, right? And this main grid is connected with this microgrid through this local controller, and this its local controller is connected to a microgrid central controller, right? So in grid connected and islanded mode both, each DER is connected with its powertronic interface to achieve control, metering, and protection objectives. Together with an ability of plug and play feature, it can be added, it can be removed whenever required, and as and when required. So we can also see that here some weather forecast is also visible through some connection to the MGCC, and this energy market is also connected to this MGCC with this microgrid, and controlling is done by this MGCC. So this grid connected mode, a microgrid reaps advantages of power trading also with the main grid. But in case of disturbances or failure in main grid, microgrid shifts its operation to islanded mode to ensure system stability. But when in this grid islanded mode, it provides continuous supply to critical loads by efficient integrated operation of distributed energy resources. It also uses demand response, and it also uses the phenomena of load shedding. So this entire operation of this microgrid is controlled and coordinated by this MGCC, central controller, and these local controllers. Local controllers are there with each and every resource, and this coordination of this local controller and the central controller runs the show efficiently and effectively. And this effective management and coordination of DERs in microgrid results into improved system performance and sustainable development, which is the target of this United Nations program also. This diagram gives you a comparison of this centralized controller, decentralized controller, and distributed controller. The very first, I will try to explain this centralized controller. As I told you, as I have shown you in the last diagram, there is a centralized MVCC and the local controller with each DER, right? So this local controller with each DER, voltage source is there, load is there, and they are all connected and they are interacting with each other through this MGCC, right? And this MGCC coordinates and manages the DERs in the microgrid. The control loop is usually processed in 3 steps. Local controllers monitor the operating states and local information to be sent to MGCC. Based on the MGCC global information, MGCC calculates the system's optimal set points and sends them to individual TER controllers, these local controllers, right? So all the information reaches to this MGCC through these local controllers, and all this calculation and decision making is done by MGCC centrally for all these controllers, which is implemented through these local controllers to their individual DER. And this centralized control, for the centralized control, this is connected to the main grid through this control switch. And this individual DR controller receives the control commands and execute accordingly. Here I have written this resource reference, but I do not know how this is not visible right now. That I can modify later. And here in this diagram, you can see that this red is the measurement and communication. This blue one is the control command, and this without dotted line or full line is the electrical network. So the difference between this decentralized and distributed control, the similarity between this decentralized and distributed control is there. Both of them lack this MGCC, means no centralized controller is there. But the difference is there, this decentralized control and distributed control. In distributed control, there is a flow of information, of measurement and communication between these distributed controllers. But these decentralized controllers, they do not communicate with each other and take decisions. They may be, they do not have interconnections, and they take these calculations of required data and decision making at their local level. And that is the reason when we compare these matrices for these different types of control, we can easily conclude that the responding speed is lowest for the centralized controller, decentralized it is the highest, and distributed it is this medium, because there is a communication between decentralized controllers and these distributed controllers, right? And but just because of these calculations made by a single controller, the control accuracy is highest for this centralized controller. For decentralized, it is the lowest, and for distributed, it is medium high. Definitely, on the same basis, we can also conclude that the computational complexity is also high for the centralized controller. And similarly, it is low for decentralized and distributed. This complexity is lower. Then communication burden is high for centralized, low for decentralized, because minimum communication is taking place, and that is limited up to the decentralized controller. No further communication is there, right? But in this distributed, it is medium high, because it is having communication between the decentralized controllers also. That's why we have given we have termed it as medium high. Then the stability of centralized controller is low, decentralized is high, and distributed it is medium. Economic performance wise, this centralized is medium, decentralized is low, and distributed is medium high. Definitely, this scalability, if you want to multiply it as a modular expansion, this scalability is medium for centralized, medium for distributed, but for decentralized, you can scale it up to any level, and definitely this is scalability is high for decentralized. I hope you are clear vision about this difference. with this. After this particular table, I can show you the diagrams once more. And this is centralized with this MGCC, where each and every local controller that is connected through MGCC with each other. Decentralized controller, every control information is coming or going from this decentralized controller. No interconnection between them. But in case of distributed, this information means these distributed controllers are communicating. There is no MGCC, but they are communicating information with each other. So this is the difference is the basis of this comparison between these three types of control. And when you say that these are three control layers of these hierarchical controls layers, they are primary, secondary, and tertiary. And their time scale is also from milliseconds to minutes, right? So definitely the primary control is taking care of control goals of power balance, power sharing, and synchronization. Secondary control is taking care of goals such as frequency regulation and voltage regulation, whereas tertiary control is taking care of control goals such as economic power dispatch and battery energy management, right? But in case of this is that differentiation between these all three levels of hierarchical control. But if you go through these available literature, right, you will find that decentralized and distributed control approaches, they use all three control layers in them, right? So this makes it a bit typical, but this is a common practice of using all three levels of control layers in these two types of controls, which we have shown later. First was centralized, second was decentralized, and third was distributed. And this is again a summary from another paper, recent paper of 2021. It clearly indicates that this primary control stabilizes the voltage and frequency of microgrid by implementing fast-acting voltage and current control loops, operation cycle time, and that is in milliseconds, right? Central control, it says to compensate. Secondary control, it says to compensate the residue deviations of omega and voltage after the execution of primary control. Operation cycle time is millisecond to seconds. And this tertiary control that goes in the operation cycle time of minutes to hours. It takes care of ensuring optimal power flow and economic dispatch, regulating the active power and reactive power, and maintaining the synchronization of the system. Okay, so views are a bit different in different research papers, right? They are giving their observations on the basis of their findings in their research, but basis of all these classifications of levels and other control requirements, I think that is almost same. So if we try to summarize the different methods and their functionalities, that is shown in this paper, and this is also a recent paper of 2022. It clearly says that the methods are primary, secondary, and tertiary, and their respective functionalities, they are also listed parallel to them, right? And it clearly indicates that the time requirements of response time, they are varying between milliseconds to minutes, right? And the functionalities are similar as we have already discussed. And all these three controls, they are interconnected through measurement signals, and control signals means flow of information and control requirements and measurements and monitoring that is always present among these three control levels, right? So you can understand this also. If you have any question, you can ask, right? I will like to move ahead now. So this is a comparison of the supervisory controller, and it says that this, in case of centralized control, Local controller is dependent on MGCC for decision making. Advantage is that MGCC allows economic implementation and easy to maintain. Disadvantage is failures of control, central control affect the whole system operation. If MGCC fails, whole system fails. Means LCs are not capable of making decisions. They are simply responsible for implementing the decisions made by the MGCC. Second advantage is for whole MG system, a strong controllability and real-time observability is maintained. But in parallel, you can see that there is a disadvantage of low flexibility and expandability or further scalability. Provides strong supervision but requires higher data interchanges, and that's why more complex in computation and data requirement and time consuming processes are there. Offers high performance computing units, requires, which definitely this advantage requires a high processing unit for central controller. So that is also a complex requirement which is quite computation intensive and cost intensive also. Then another advantage is secure communication infrastructure, but definitely this degrades the reliability of the whole system. The optimal decision is guaranteed. That is the advantages of using MGCC in centralized control strategy. In case of decentralized, LC provides its decision making individually and they are nowhere interconnected, as you have seen in the diagram, right? So these LCs are responsible for decision making as well as implementing, right? So this has increased reliability and robustness, avoid single points of failure. Means in case of failure of any local controller, only one part of that particular DER is not working, right? But remaining DERs are sufficiently capable of giving their services. Autonomous control capability, high privacy for the DG unit. Excuse me. Just a minute. And this high privacy for the distributed generation unit means no information is being sharing of the about that DG with any other DG or any other controller. So minimum amount of information is being shared between the controllers, right? And they can be easily, new units can be easily added or units in service can be easily removed, right? So this functionality of plug and play that can be easily realized. These are the advantages of this decentralized control, but disadvantages are incomplete information about overall MG status. Yes, it is there. Not guaranteed global optimal results for the whole MG system because nothing is being shared with other controllers. Implementation complexity is there. Yes, requires effective synchronization and strong communication as sharing is not there. Then comes the hierarchical. A local decision is made by the source converter. Voltage and current are regulated locally by the converter. Flexible regulation of the system voltages within acceptable limits. Improve current mismatches among the controllers. Combining previous control structures, the optimal decision is possible. Yes, these are the advantages with the hierarchical control. If you want to read further about the hierarchical control, you can read this paper of 2022. This is Journal of Kernel Production. This will give you an insight about this hierarchical control. Definitely a good paper. You can read it. Then disadvantages are fewer computation burden, fail to transfer energy or information if there is a fault in upper layer. So then information cannot be shared and it cannot, information processing is not complete. An intelligent system is required to forecast the demands to achieve generation balance, and that increases the complexity also. So different control approaches which are already implemented in this MD system, they are being summarized in the same paper of 2022 of Journal of Clean Production, as I told you. So they have compared different control techniques such as conventional troop control, FLC based control, and adaptive troop control, MPC, multi-agent based control, ANN based control, PI controller, hysteresis controller. So all of these are compared in that. Uh, just because of time is limited, so I will simply go through it. But I can refer you this paper of 22 of Journal of Clean Production. You can go through it if you want to go about more details considering stability, objective, and constraint issues. Right? A good summary is presented there. And if we talk about the newer generation of controllers, which are data with the availability of data, the new techniques are artificial intelligence and machine learning techniques, which are to be implemented for microgrid control. You can take them in different directions with this machine learning in unsupervised, semi-supervised, supervised, and reinforcement learning, right? And this unsupervised you may find application in terms of dimensional reduction and clustering, whereas supervised may be used with this classification and regression, right? So these are the few control techniques, and there is a sufficient literature is available on this. Summary of this such literature of application of AI and ML for microcontrol is given in this 2022 paper of Energy and EI. It with the title Implementation of AI Techniques in Microgrid Control Environment, and it discusses the current progress and future scopes of these AI-based controllers for microgrid control. The same paper gives you this complete diagram of the control strategies of different centralized, decentralized, distributed, and hierarchical control, right? And these controls may be used with power flow management, energy management, autonomous market participation, consumer-prosumer segmentation, energy forecast, power sharing, protection and tariff, protection and fault restoration, voltage and frequency control, high speed communication, and this MPPT control with different RES. For example, they have taken only power, this photovoltaic and wind, right? So this is a complete summary with the application of different control techniques for these different specific applications. They are being presented in this diagram, which is taken from the similar paper of this 2022 of Energy and AI, right? As I given in the last page. So these two diagrams are listed here from this paper. I recommend you to go through this unique paper. You will not find such informative paper with any other publication in the recent past. So this is, I think, the recent available literature. There are so many papers available for different aspects, but for control with AI applications is this paper only. Then comes this microgrid energy management. We know that in what is energy management. Energy management is basically a balance of generation and consumption, means energy supply and energy demand. And this energy management is a software platform which provides basic support services and a set of application, so that the MG can ensure the adequate security of energy supply at minimum cost, right? So this optimization is performed, we all know that in this case, for maximization of profits and minimization of losses, right? So this microgrid energy management system consists of modules of distributed energy resources, load forecasting, generation forecasting, human machine learning interface, then supervisory control and data acquisition using SCADA, among other resources, or some other options are also there of these modules. So what is the role of energy management system? Energy management system in microgrid improves system performance, reliability, and system energy efficiency. And it reduces energy consumption, system losses, and operational cost of distributed energy resources. Also, it mitigates greenhouse gas emissions. And if we summarize these all these things of all these roles of energy management system, we can find it as this particular diagram shows you a clear picture of the energy management strategies of microgrid, right? These green blocks, they show you the objectives considered. These are the different components which are taken as a part of the objective functions, right? And the red blocks, they represent the constraints considered, typical constraints for microgrid operation, and green are the objectives. If you list them, you will find them that most of them are quite, you are aware with them, or most of them, like objectives are energy transaction cost, battery degradation cost, outage and interruption cost, demand response incentive, losses cost, load shedding, greenhouse gas emission cost, operation and maintenance cost of energy storage system, levelized cost of energy of renewable resources, and operational and maintenance cost of conventional generators, CGs, right? So these are the objectives, which are the components of the objective functions, right? You take a combination of these objectives in your objective function. But you also consider the constraints also to make it an optimization problem. The constraints may be network constraints, energy balancing, output limits of renewable resources, demand response, reactive power support, reliability, physical limits of conventional generators, and physical limits of energy storage systems. So these are some standard constraints and objectives which are usually considered for this microgrid energy management system operation. So one more thing you will find that this is a very typical summary observation. You can say that whenever we talk about this microgrid management, right, you will find that there are two types of management. One is control and second is energy management, right? So this energy management, basically that conditions that includes all those constraints and objectives, and then they form a multifunction or single function objective function, and which optimizing function subject to constraints, right? So this is the shape of the energy management problem, and then they try to find a global optimum solution. But in case of control, you will find that the control is for frequency control or voltage control, active power control, reactive power control, and so many other targets are considered for control, and they are done for this grid connected and islanding, these two types of operation. And for grid connected, there are decentralized and centralized operation, whereas for islanding, this PQ control is used. And for this grid connected, they are VF control, master slave control, group control. We have already discussed these things. But this particular differentiation of microgrid management between energy management and control management, it clearly indicates that the trend of, as per the trend of the available literature, the energy management has been investigated more than control aspects, right? The control aspects is yet to be explored for more efficient and more effective objectives or fulfillment of objectives, you can say. So this is still has a scope, and I motivate all of you to contribute your research contribution and make your research contributions in that direction. And then comes the concept of multi-microgrid also, where these different microgrids, they are also locally controlled themselves, and then they connected to a they form a multi-microgrid system for the fulfillment of larger objectives, right? So this is a different scope. We can take it some other time in future, but definitely The control requirements of the hierarchical control, they are almost similar. There are primary, secondary, tertiary control for each and every microgrid, which are the part of this MMG structure. I think there is sufficient time. The time is almost up. But let me tell you one very interesting article about this practically implemented microgrid. This microgrid is implemented in Illinois Institute of Technology. And I have taken this information from this IEEE PES magazine article of 2014, right? So this is an article by M. Khodyar and M. Shahidpur. This is a very interesting article. You must go through it for which gives you a story of successful implementation of primary, secondary, and tertiary control of microgrid, practical microgrid in an academic campus, right? And it clearly, this particular diagram clearly shows the objectives and functions of the operation and control, right? The microgrid components used for this particular example are coupling switch at point of common coupling, meters and PMUs for monitoring and in transferring of the data, building controllers are there, HRDS switches are there, gas turbines are there, battery storage is there, solar PV, wind turbine, they are the component, right? And primary control is there implemented between these components, right? But this secondary control that gives you the set points for the primary control, and this monitoring and control is also done by this secondary control, right? And the secondary control that indicates that consists islanding and desynchronization information, emergency demand response, as well as making self-healing decisions, as which is the property of a smart grid, right? That is being implemented in secondary control. And definitely the tertiary control is used for its coordination with the main grid, right? And it decides the grid connection and islanded mode selection, definitely using this coupling switch of microgrid, right? So these are the three control levels of this practically implemented microgrid, and this microgrid is performing this economic operation as well as reliability operation for that particular campus network, and fulfilling the requirements or the characteristic requirement of the microgrid, right? Uh, Definitely, I would love to explain it, but I think the time is not permitting us now. So you must go through this particular article where this master control is there, which is coordinating between all these components and different control units. Please go through this article of 2014 January February issue of IEEE PES magazine. So there are deployment of microgrids. There are different type of deployments, campus and institutional. As I given you an example of academic campus, then military microgrid, residential microgrid, remote and rural microgrid, right? This particular classification or some different examples. They are initially, I have taken them from this 2016 paper, publication of renewable and sustainable energy reviews, but definitely we have added more to the list, and this is a complete list showing you a complete list of renewable energy based microgrid projects, right? And one of them is the very famous example of Santa Rita jail microgrid, which was started in 2002, quite old and quite still working very successfully, right? So there are some other examples also in India. We are also having this LNT Chennai campus, and some other examples are also there in India, which have been recently added, but their capacity wise not they are that big. so we have not included in them here, right? But as you can see it here, the cost of implementation of microgrid is too high, right? You can see it here that this is the capacity of renewable resources, total capacity, and for this 2019 cap cost is around 14 around 15 million dollars is the cost, right? So definitely this is a costly affair, and microgrid, but that is the need of the future to fulfill all those requirements which are to be taken care as an target of United Nations program. As I was talking about this Santa Rita Jail smart grid, this is situated in Dublin, California, right? This is a remote island away from the mainland, right? So this is USA's largest CERT-based energy. We have already discussed this CERT. So CERT is a protocol of microgrid which is being followed in the United States of America. So this has renewable energy generation, large-scale energy storage, and constructed and designed by Chevron Energy Solutions, right? So what are the components? This is having 1.2 megawatt rooftop solar system. This is having 1 megawatt fuel cell power plant, 5 wind turbine, each of 2.3 kilowatt capacity, 2 emergency backup diesel generators, each of 1.2 megawatt. This is also having this 2 megawatt advanced energy storage systems with a islanding this sub-cycle static disconnect switch of capacity 12 kilovolt voltage level, right? So this is the control switch. It means it is getting a voltage supply of this voltage at this particular voltage level, right? And this is equipped with electric power export and import capability, right? And if you want to read more information about it, it is already available on the government website of United States of American website, acgov.org. And there you can get for this SRJ Santa Rita Jail Smart Grid overview. It is already available on that website. And this is not a new system. This is working since 2002, means almost 2 decades it has completed. And interesting thing is that this fuel cell power plant also gives this CHP capacity, combined heat and power capacity is there. It is equipped with that. So what are the future trends in microgrid control? There is a time when microgrids are going to be a requirement. So more microgrids are required. And when more microgrids are required, so definitely it is going to be a system of multi-microgrid, and their operation and control is going to be a future trend. Soft switches applications, meta-heuristic optimization based control, load management, these are the problems, these are the trends which are to be addressed in future. So what are the challenges now? Challenges are legal and regulatory uncertainty. There are several countries which are still not having regulations about the microgrid implementation. So there are microgrid, they are just as a showpiece, but they are not having those regulatory permissions to participate in market, XD market, or gain the complete potential of the advantages available with microgrid. So that is also a challenge for the coming time. So I hope in the coming time, all the countries or all the territories or all the power corporations, they will have some regulatory requirements for them. Then their interconnection policy, because when you are going to use them as a source or load both with their connection at PCC, so this interconnection policies shall also be a part of requirement in future. Utility regulation, accordingly, this utility regulation shall also be there, which may define the economic requirement, policy-based requirement, and other participation requirement of these microgrids. And definitely the utility is also going to have the opposition, right? Because this generation uncertainty is always there, which is definitely going to be a limitation or a challenge for the utility. There is an article in 2003, I think, that was the spiral death, utility spiral death. This is a very important term. You can note it and read it, Google it further. That is utility spiral death, right? That is a term which has been, which was used by a newspaper article, but definitely this is a technical challenge for networks, utilities, which are having more number of prosumers in their network, right? And this increasing number of prosumers with increasing capacity of participation, that is going to be a threat sometime for the utility, right? So this is definitely a potential challenge for participation. Then comes the future prospects and open questions. So this all is going to be a part of upcoming smart grid things, or its smart grid infrastructure. So their compatibility is always a matter of concern. Means a smart grid shall be capable of including these microgrids within them, right? And accordingly, the market structure and degree of market decentralization is also a concern, which is also a requirement of microgrid, futuristic requirement of microgrid. Because in the coming time, you will find that this energy market is going to be one of the largest market across the globe, right? So these things definitely are to be in consideration if we want to be a futuristic in our thinking, in our approach. So there was a conclusion. In conclusion, I will simply say a quotation by the former chairman of Motorola Corporation, Mr. late Robert W. Galvin. They say that perfect power microgrids will ensure absolute and universal availability of energy in the quantity and quality necessary to meet every consumer needs, right? It is a system that never fails the consumer of electricity, either from the urban area or from the rural area. So here with this, we can conclude that the microgrids are definitely going to be a major source of electrification and fulfillment of electrical needs for every consumer throughout the utility domain, either in rural or urban area. They are going to be a customer for this microgrid. They are going to adopt these microgrids for their electricity requirement. So, and definitely we can find that in terms of reliability, it is already published, literature is full with this remark that reliability, wherever the reliability is required, wherever the environmental fulfillment of environmental concerns is required, the microgrid need of requirement is easily justified. So with all these comments or conclusions drawn from this particular lecture, I will like to end this because still the research is not complete. Research is a continuous process.
Sir, on the behalf of the Albag Education Institute, Agra, we will be happy to offer the e-memento for you. Thank you very much.
Thank you, sir. Thank you. Thank you very much.